All right, let's be a little bit faster for part D since we got the rust out of the way, so we know what we're gonna do. So we're gonna write a n equals fn. That is n over n to the fourth plus 1, so that allows us to grab f of x to be x over x to the fourth plus 1. Since n starts from 1 in the sum, so I'm going to go ahead and then choose x's to be starting from 1, okay? X is greater than or equal to 1. All right, so let's check the conditions. Well, is f positive? Well, in its domain, which is x greater than or equal to 1. Top is positive, bottom is x to the fourth plus 1. That is also positive, so let's put a check mark here, okay? Again, for x is greater than or equal to 1. This f is positive only for that, okay? Is f continuous? Well, it's the ratio of two continuous functions, and there's no x making the bottom 0, so the bottom doesn't get to 0 for any x. So we're safe, so the quotient is continuous. Check mark. Is f decreasing? Well, we have to check. Check what? F prime, right? Sign of f prime is going to tell us if f is decreasing. So let me just do that real quick here. So f prime is going to be what? We're going to use the quotient rule, okay? The derivative of the top, which is 1 times the bottom, minus, keep the first, keep the top, and take the derivative of the bottom, which is 4x cubed. All divided by x to the fourth plus 1 squared. Okay, so this is x to the fourth. This is already 4x to the fourth, by the way. So let me just clean this, and let's write this in one shot. Negative 4x x to the fourth plus 1x to the fourth. That's negative 3x to the fourth plus 1 divided by x to the fourth plus 1 quantity squared. Okay. And in this case, even if x equals 1, the top is always negative. The bottom is squared, so it's always positive. So this is negative for x is greater than or equal to 1. This is the first derivative test to conclude what? F is a decreasing function. Okay. So we're safe within this interval, 1 and infinity, 1 included. Okay, so we're going to go ahead and check the integral from 1 to infinity of f of x dx. All right, that's what we're going to look at. But first, we have the indefinite integral version of the improper integral. So I would like you to pause the video at this moment and start thinking about what technique could be applicable to integrate this function. Okay, so think about it, and I'm going to show you in a sec. All right, first of all, why don't we write the bottom as x squared plus 1. Okay. So this allows me to call u to be x squared, so that du is going to be 2x dx, okay? All right, x dx is over there, so this integral is converted into 1/2 du over u squared plus 1, which is a known integral, right? So this is 1/2 arc tan u. Okay, I don't need to worry about plus c at this moment. 1/2 arc tan x squared. Okay, so this is a nice u substitution problem to convert the given integral into something that you already know how to integrate. Okay, so going back to this integral here. Okay, so I have 1/2 arc tan x squared, and I put the limits 1 and infinity, but the limit infinity is going to be taken in the limiting sense. So essentially, when you plug in the lower limit, that's going to be arc tan b squared minus 1/2 arc tan 1. And we have the same, almost the same case like in the previous previous exercise. So what is arctan for a large number of inputs? So arctan infinity. So that's going to be pi over 2. So let me just continue from here. Okay. So 1/2 times pi over 2. And arctan 1 is something that you can use your calculator for. So 1/2 pi over 4. Okay. And that takes you to pi over 8. And pi over 8 is a finite number. So is this integral. I can go ahead and write this is less than infinity, so it's convergent. Okay. That's good, because if that integral is convergent, we can go ahead and conclude that this series is convergent by using the integral tests. Okay. Alright, this was a long video because I wanted to put all different examples for you to see how the integral test is applied, rather than just giving you one exercise to work on. So I think you have seen all alternate versions of infinite series and how the integral test is applied. I'm sorry that the video was long. So thanks for watching. I'll see you in another video. Bye.